Um, so today we're talking about hypergraph categories and operads. We'll do a lot of like limits and colimits stuff, but wanted to start by talking about, so kind of the motivating thing in this chapter is circuits, electrical circuits, I guess. And here's a picture of a flip-flop memory diagram. You've got 6 ports on the outside, and resistors and transistors and voltage, well, and ground and all sorts of different things. And so one belief you could have is that if you find any kind of systematic way of doing diagrams in literature, in scientific literature, that it's a good place to look for a category theory. And so in this, today we'll see that this kind of diagram, well, I'm not sure I'll really get into it much, but I guess I'll say it right here, that this kind of diagram, there's connections and there's things that are kind of being connected. And those connections, unlike pictures we've seen before, are not directed, for example, so it doesn't feel like a monoidal category exactly. And yet, there's things being connected, and so this will be kind of abstracted into what's called a hypergraph category, where this will be the sort of way of composing different morphisms. Each one of these transistors will be a morphism, each one of these resistors will be a morphism, and this will be a picture of composing a lot of morphisms together. So instead of composing morphisms in a line, where you're allowed to kind of, in a category you can compose morphisms like this, in a monoidal category you can compose morphisms in series and parallel. And in a hypergraph category, but in both of these, the wires are directed. And in a compact closed category, like we talked about with co-design, you can have feedback, but there's still a directedness to everything. In this world, there's no directedness. Voltage flows as much forward as backwards. And so we want to kind of picture language, diagrammatic language, where these make sense, where each of these little bubbles is, say, a resistor or a transistor between various things. And to have a diagrammatic language for these, and then you can have syntax. Those would be syntax. There's also semantics. So Brendan and John Baez proved that, like, if you're only looking at passive linear circuits, which are resistors, inductors, capacitors, then there's a functor from this diagram, diagram language to the category of Lagrangian relations. More generally, there'd be a functor from the category, from like the hypergraph category is called. This is a hypergraph picture. So. From the hypergraph category of all circuits to the category of relations. You'd say this component means this relation, and all of them are satisfied simultaneously when they're all interconnected. So that's how you kind of go from picture language to semantics to, say, category of relations. That's the idea today. But that's the motivation, I guess. But what we'll really focus a lot of time on today is limits and colimits. So. We've talked about this a bit, but we need to go into it more deeply for both next time and for the topo series stuff. So, diagrams in categories. So you might have seen, like, in any class that uses category theory, you'll see commutative diagrams. So someone might say that they have a commutative diagram, A, B, C, D, and this commutes. So this is some diagram in C, and you say it commutes. But we can understand diagrams in terms of functors. And we've said this before, but I'll just say it again. So an I-shaped, so definition, and let's C be a category. And I is also a category. It's called a small category. You can think of it as like a finite category, or just a category with a set, like a set of objects. But I am writing I capital because, or non-script, because it's serving a slightly different role. It's the shape of the diagram. An I-shaped diagram. And I stands for indexing category, I guess. You'd say that I is the indexing category of this diagram. In C is a functor. D for diagram from I to C. So what is I, if this is a commutative diagram, what is I here? What category is it? Any ideas? In this case, well, it's a category with 4 objects and I think 9 morphisms, 4 identity morphisms, and let's see, 4 identity plus 1, 2, 3, 4, plus the composite where I force that this way and this way are equal. And that's a category. And a functor from this thing to C assigns to each object here an object of C. So it might assign A to this one, B to this one, C and this, and D there. And it assigns a morphism for every morphism in I. And so it just redraws this picture in C. So if C is the category of sets, you might have natural numbers mapping to the natural numbers, mapping to the integers, mapping to the natural numbers. They don't have to be 4 different maps. This could be the identity. This could be times 2. This could be minus, so you send 5 to minus 5. And this could be times negative 2. And if I'm, yeah, I think that looks good. And it commutes.
One's not a map.
What happened? Uh-oh.
Kind of
Well, let's do
absolute value.
times 2 absolute value. Is that good? Okay, thank you. X maps to absolute value of 2x. And this diagram commutes, so you don't have to be 4 different objects. I could have just done identity, 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 identity between naturals 4 times. But this is a functor from this small category there to C the category of sets, say. And I guess I could continue this definition, a morphism of diagrams. So if I have 2 different I-shaped diagrams in the same category, then you could probably guess by the picture I just drew what I'm probably going to make the morphisms be. The morphisms are going to be the natural transformations. So the goal of today is we should understand what that's talking about. We've already defined natural transformations, so I'm not going to do that again. But we're going to talk about what that kind of looks like, and more importantly, we're going to talk about kind of special diagrams and special natural transformations called limits and colimits. So one more thing, if C is an object, if you have this object, a lot of times in math, I don't know if everyone knows this, but in math grammar, it's typical to kind of write something symbolically and then out. In English. So if C in C is an object of C, someone might write, then the constant diagram, this constant I-shaped diagram on C, or at C, I don't know, on C is, well, it's a functor from I to C, but what do I want to use? I'm going to go down to the one object terminal category 1, and then up, let's see, let me try to say this again. We once saw that objects in C are the same thing as morphisms from 1 to C. 1 here is this little category there. So if I had a functor from 1 to C, that's an object in C, just like this is 4 objects and 5 and 9 morphisms or whatever. So we have this with this object in C, but there's a unique functor for any other category I. There's a unique functor to 1. It sends all the objects to 1, and it sends all the morphisms to the identity. So whenever you write an exclamation point, that usually means, of course, we've been writing F lower shriek, which is an exception, but usually people use exclamation point to mean there's a unique one, and I don't need to name it. I think in functional programming you might just write a dash or something, or an underscore or something. I don't know what they do. But if there's a unique one to unit type or whatever, you write an exclamation point here. And so what we're saying is that the constant diagram on C takes every object in it, and sends it to a single point, and then sends that point into C. So for example, when I said the constant diagram on N would be this one. for whatever shape I have, the constant diagram sends every object to the thing called C, and it sends every morphism to the identity on C. Do you guys see how this way of writing it, a functor from I to C that factors through 1, is accomplishing this constancy condition? Some people look happy, some people, okay. See more nods. Yes?
So the diagram can be anything, not only the commutative square.
Here, I'm doing an I-shaped diagram, so you fix your I, but no matter what the shape of I is, so I could be, I don't know, that shape. I have a functor that sends every dot in that to the single dot, every arrow to the identity, and then I have this map to C, to the natural number, to set, say, that just sends everything to the natural numbers. Now all 3 of these will get sent to the naturals, all the morphisms will be sent to identity. Okay, so that's what a constant diagram is. And so I can define what a limit and colimit is using what are called Conn extensions, which sounds even more complicated, but I'm doing a very simple case of it. So definition. So let's say you have, again, let's C be a category. Well, I guess C and I are both categories. And I to C is some diagram. It's an I-shaped diagram in C. Its colimit is an object colim D. That's the name of the object. It's got a long name, colim D. It could be called Q, whatever. Is an object colim D together with a natural transformation. So we're going to take this definition and then unpack it and give you lots of different examples. And what is a natural transformation? Well, we have I to C. This is the diagram D. It's this commutative square or whatever it is. We have this unique functor to 1. And now we get this colim. Someone gives us colim D as an object in C. And they also give us a natural transformation, say Q. From, when you see this picture here, it means that there's a natural transformation from D to the composite, where colim D is initial with respect to this. I don't know if we've talked much about initial and final objects. But what that means is that for any other thing, if someone comes, the bad guy comes and he gives us, or she, gives us another functor from 1 to C called dolim D, and they think they're the ones. And they also give us a Q prime from D to exclamation point dolim D. Then we will be able to show them that we are first in line, that we can get a natural transformation from our thing to their thing, such that Q prime is the composite of Q and this guy. So whatever they find from D to theirs, we can factor it through ours. We're like the initial universal gatekeeper of this thing.
We're the smallest?
We're the smallest, yeah.
Colim D unique?
Colim D is unique up to isomorphism. Yeah. It's not, when I say smallest, it's just for intuition purposes. Yeah.
So is this an initial object in like the functor category of like this triangle-looking diagram?
Yes.
Is that okay?
Yes. It's the initial object in the category of all functors from this to this that come equipped with a natural transformation Q.
So in particular, this map from colim D to dolim D should be unique.
Oh, sorry.
You said that.
This map is unique. Yep. Yeah. This is unique. There's a way of expressing this more formally if you wanted. Namely, there's a map from what am I talking about? Oh yeah, there's a map from C to the I, from C to C to the I, that uses the constant diagram, takes any object in C and returns the constant diagram of shape I, like we talked about there. So if natural numbers will go to nat, like form identities. That thing has a left adjoint, and that's colim. That's another way to say it, if you like adjoints. This is the one that's going to be easier for us to talk about, even though it looks complicated right now. Limits are pretty similar. Its limit is an object lim_d, that's just the name of the object, together with a natural transformation that goes from I, let's see, you have D, you have the thing, the unique map there, you have lim_d, and you ask for it to be going the other way. We'll make sense of this in a second. So we have this P map, and it's final, such that lim_d is final, or terminal. So if someone comes and gives us mim_d, and a map from that to D, and we will be able to factor theirs through ours. We're the universal gatekeeper, we're the closest one. We're the closest one to D that factors through the one object, category 1. Basically, we're a one object summary of D. These are two different ways of taking D, which is like this big, multiple objects, multiple arrows in C, finding a one object summary of it, that the fact that it's a summary is encoded in the fact that there's a natural transformation. So it says, all the data that's there, I know how to interpret it in your summary. Or all the data that's there, I know how to interpret your summary in it. And it's the best possible summary for a one object category, in that sense of summarizing. If you believe that's a kind of summary, then it's the best one. Okay, so any questions on that?
Is it possible in D, the
Yeah.
objects that are in the diagram not necessarily be the same object? So for example, here we have like N, Z, N. Could that be a D?
Here, this is, right. So what are you saying? Sorry.
Yes.
So here, let's say we call, I has 4 objects, A, B, C, D. Then D of A, well, is the naturals, and D of C is the integers. Does that help?
But then how do we know to like but when we like reduce it to the one category, like we lose the data of what object or what were the objects.
Yeah.
So D doesn't have to factor through 1.
Yeah, D is not, this diagram does not commute if the Q isn't there. The Q says I have a natural transformation from this functor to this composite functor. So D isn't having to factor through 1 itself.
So we've seen an example of this sort of in meets and joins and in products.
Yeah, I'm going to do meets and
so
joins
yeah,
pretty
so maybe
soon.
that'll help.
Yeah. So maybe I should say kind of what P and Q are doing and then give a bunch of examples. Okay, so what is all this stuff? This is saying, what is Q, for example? It's saying for each object I and I have this, we have, from the diagram, we have D of I, right? That's like the naturals or the integers. And we have a component called Q sub I, because natural transformations come with these components. For every I and I, we get a component from D of I to colim of D. So all these different DIs map to the same object, colim D. So what does the element I go to here? It goes to the one object there. Everything does. And that goes to the object called colim D. So that's what this natural transformation does. It goes from, for each object here, it goes from that thing to that thing. And for each, if you have a map F from I to I prime in I, the diagram commutes. So what diagram commutes? d of I, we have d of I prime, and here the map is called d of f. It's something like x goes to 2 times x. That's what's happening right there. And then we have a map called qi that goes to colon d. We have a map called qi prime that maps to colon d. And then what should we have here? Well, we're supposed to have the component of this, we're supposed to have this functor applied to f. But this functor, if I have an f in I, every morphism in I gets sent to the identity there. And the identity always gets sent to the identity, so this gets sent to the identity subcolon D. Okay, so we're saying that this commutes. It's like we've taken the whole of I, we've taken I. So I is some weird category. Maybe it's a square. Who knows what shape I has? It's some weird category. Here's I. And we've taken all, and we have this functor called D. And D sends it to like A, and F, and B, and all sorts of stuff in our category. This is occurring in C. And now this other thing takes us to just like colim, 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 identity, 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 identity. And then this Q is saying that A maps to colon, B, so A maps to colon, B maps to colon, C maps to colon, D maps to colon, and everything commutes. So it's kind of just copying that diagram with the same thing over and over, the single summary. And all these guys are mapping into the summary, in, and all of the diagrams commute. So if you have B mapping into the summary, and then going down like that, it's the same thing as going down like that, and then into the summary. That's what the naturality means, yeah.
Why are you calling it a summary?
Let's see, so let's do some examples, and hopefully it'll become clear. I don't know if it will right away, but maybe hopefully soon. So in post sets, it may not, in post sets, we already saw that joins are colimits and meets are limits. So for example, we're now calling the max of 5 and 6 the summary of 5 and 6. It's like, for someone's purposes, max could be a summary. And for someone else's purposes, min could be a summary of 5 and 6. And for someone else's purposes, GCD of 5 and 6, or LCM, these common multiple of 5 and 6, could be a summary of what are 5 and 6 really giving me? They're giving you 30, you idiot. I don't know. Like when you're trying to summarize 2/5 plus 3, 6, you like summarize what's the common thing here? Well, I don't know how to do it, but 12, 15, 24. Okay. This is some kind of summary for that purpose, right? Because you want them both to live in one common place. And so, yeah, so it's that kind of summary. It's not a great word. I'm not really standing behind that intuition too much, but it's a kind of way to see it. So if you have this, so in that case, maybe you have two, here's your I category, here's your post set, and maybe your post set looks like this. This is the Hasse diagram. Okay, and then you have some kind of functor, here's D. Okay, now what is the limit of this? How far am I doing? No idea. Okay, so what's the limit of this? Well, it's some single object. So I've got to find, so now I have this kind of single object thing there called 1. And I'm trying to find some map from 1 into this thing and a natural transformation that way, which means that if I take anything here, send it down to 1, go in here, I'll have that says I have a map from that thing to the original. So it's something, if you're going to find a summary, it could be like this, or it could be like this. Both of those would work, because in both cases, I'll have for either one of these, I'll have a natural transformation or a component that takes what happens this way to what happens the other way. So the only possible, like, Q there, even the colim or the dolim or whatever imposter or other person who thinks they've got one, they're going to have to land down here somewhere in order to have this natural transformation. But this one is the best possible one. It's the closest to these two. So it's the meet, and it's the limit. So this guy here is the limit. I guess I should have colored it. And I guess you can also guess the colimit. The colimit needs to have a map going from D. I mean, just to draw the thing upside down, but oh well. Has to have a map from D to it. So it's above those two dots, and it's the closest thing to them. Any questions about seeing? What I want you to do here is, we already talked about joins and meets in terms of limits and colimits a little bit, but that diagram up there looks scary at first, and I want you to see it here. Do you see it enough here? Okay, kind of. Getting the kind of sign. This natural transformation is there and there, depending on which component you're at. That's a component, that's a component. Okay. Let's do the category of sets. So I'll give you a general, in set, which is the category of sets, there is a all-purpose formula, I don't know, a general formula. For both the colimit and the limit. So I'll give you the one for the limit now, and then I'll let you work out the other one in a second. For the limit of any diagram. So if someone has a diagram, it's a pullback, it's a product, it's an equalizer, it's whatever kind of diagram they want. So you have this diagram called D. The shape of the diagram is I. That's the indexing category. And you have a functor to set. And these, by the way, are also called database instances for database I, if you want to recall that. The limit of any diagram, it is as follows. That the limit of D as a set is the set of all tuples. I should have written this formula down. X1, X2, Xi. What am I doing? Xi, one for each I and I, such that for all f taking I to I prime in I, okay, where am I? So this thing is in, there we go, D of X, D of, let me try again. Sorry, I didn't write this out very well. So let's say our diagram looks like this. In the book there's like a nice clean formula for this. Okay, that should be enough. I1, I2, I3, I4, I5, F, G, H, O, A, B, C, D, E, F, G, H. Sorry about that. Okay, so X1 is in D of I1, X2 is in D of I2. D of I1 is a set, D of I2 is a set, dot, 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 D of I n is a set. I'll just assume that this thing is finite, sorry. Okay, so I want one object in each of the sets that D gave me for each object in I. So we have 5 objects in I. I'm going to get 5 elements, x1, x2, x3, x4, x5. And I have to tell you, and it has to satisfy the condition that for every map from I to I prime in I, if I apply D of F to x I, it's equal to x sub I prime. So let's do some examples, because this is a terrible presentation. So what am I talking about? So let's say I is the diagram shape that's just two dots, I1 and I2. And the functor from this thing to set, D, says that we have these two sets, D of I1 and D of I2. Then what does this formula say that our product is? Well, our product is the set of tuples, so limit of I, limit of D, is the set of tuples, x1, x2, one for this, one for that, such that for every morphism in I, it sends like one thing to another. But there are no morphisms in I except for the identities. Whenever you have a morphism in I, if it's the identity, it doesn't. This condition will be vacuously held. Will vacuously hold because D of the identity will be the identity map. So this is no condition. Or if you really wanted to, you would say that D of identity sub 1 applied to x1 equals x1. And D of identity on I2 applied to x2 is x2, but that's forced. So we don't have to write it. So it's just the set of pairs, x1, x2, inside of di1 times di2. So it's just d of I1 times d of I2. It's the product. Maybe I could have said this a little better. Where x1 is in d of I1, x2 is in d of I2, xn is in d of In. So it's just the product. Okay. What about what's called the pullback? So if you have sets A, B, and C, and functors between them, this is an example of a diagram inside of sets. The diagram, what is the pullback or the limit of this diagram? This whole thing here is a D. It's a D from this shape to set. There it is there. And the limit of this, by a formula, is a set of x1, x2, x3, where, well, first of all, x1 is in A, and x2 is in, say, B, and x3 is in C. And f of x1 equals x3, and g of x2 equals x3. And this is called the pullback. So the pullback of this diagram is this other, so people will often write it like this, A to C, B to C, and the pullback, this limb thing, is here. It's called the pullback. People often write it like that. And it's going to be the set of pairs, or triples, A, B, C, where this map sends the A to the C, and this one sends the B to the C. Any questions? Yeah.
So is lim D an element of set?
Lim D is an element of set. It's a set. Yeah.
And in this case, it's a set of tuples.
Yep.
Oh.
It's a set of tuples satisfying a property.
David,
Yeah.
would you say that a good, simple intuition is the cross product of x and y as a space summarizes, in a simple way, any two paths, x of t, y of t, as a single path in the cross product space by the projections. So that as a gadget, it is a summary given the projection maps.
Yeah, I think on the very first day I kind of drew this grid of dots. And the grid of the dots is the product of this set, say A, and this set B. And in the grid of dots, it says if you indicate an A and a B, then I will give you a summary in. No, that's not exactly what you said.
Think of them as continuous.
You're thinking of continuous.
X and Y are continuous spaces and a path through the square.
That's true, yeah, so if X and Y, if A and B are topological spaces instead of sets, if you know what a topological space is, it's just, if you don't, it's just a shape. And a path in A is a function, a continuous map from a space that looks like this into A. And a path in B is a function from this space into B. And so if I have a path in A and a path in B, that's the same thing as getting a path in A times B. You can summarize the two paths.
It is a summary.
Yeah, that's right. So, yeah. Yeah, thanks. And the pullback, just to be, maybe this is a good thing since I've already drawn it. What if A and B already have maps to C, and C is a set of colors? So every element of B gets a color, say that color and this color, and every element of A gets a color, say that color and this color. Then the pullback is going to be something mapping to A and B and the colors, such that it all commutes, and what you end up getting is, let's see what you get. You get this picture. No, this picture. So it'll be, I think I said it here. It'll be a thing in A and a thing in B that agree when you look at their colors. So out of the whole grid, only this and this match on colors. So the set with 3 elements here is going to be the pullback. Why don't I let you guys discuss for a few minutes and see where we are. So turn to a neighbor, figure out where they are, tell them where you are, see if you can come to a common question.
So I mentioned this as a pyramid. It's like
I think this is just one thing, it's like the same thing we're running.
What you're choosing, the limit.
I think I'm still on
So the dots that are like separated are like on the plane, but they're
Alright.
I don't understand why I don't know the volume. In the shape back. So
Okay, any questions? Any questions anyone has? Any statements, ideas, questions, anything, nothing? Yeah.
I guess I have a question. So is pullback limited to when we're talking about sets, or
No, you can do pullbacks in any category, but you won't always have this nice formula. Like we have a, yeah.
And is it limited to when you have things like kind of in that shape?
Yes, it's
Okay.
a pullback is this shape. Yeah, it starts with these 2 arrows coming into a common thing, and it takes their limit. Yeah. Yeah, good question. Thanks. Others?
So when you say like a set of tuples, are the tuples also sets?
No, these are elements. X1 is an element of the set D of I1. Other question? Yeah.
So last time we saw that we can define colimits and limits in terms of adjoints.
Yeah.
Now we're defining them in terms of this. So can we lift this to some definition of adjoints in terms of these adjoints?
Can we define adjoints in terms of these?
Yeah.
Yes.
If the ooze is strong enough, then we can. You say yes? I
Well,
think
it's, you're defining it in terms of conic sections. These triangles are known as conic sections.
that's true, yeah.
And famously, all things are conic sections, but I'm not sure whether we should elaborate.
Yeah. Probably there's some nice way. So there's like ways, yeah, there's definitely ways of talking about adjoints as like universal, in terms of what are called universal arrows. And there's probably a way to do it this way. But off the top of my head, I don't know.
It's explained in the last chapter of McLean and somewhere in Reel's book as well, I think. Yeah.
Okay.
I can talk after too.
So, right. By the way, what happens if I is the empty category here? We want to take the colimit, or the limit, say the limit. I is the empty category, it's got nothing in it. So the functor from I to C picks out nothing inside of C. Doesn't do anything. There's a unique functor from the empty category to the one object category. And now I'm looking for this limit of the empty category, the empty diagram. What is it? Well, we need a natural transformation, but the natural transformation has no data because there's no components to look at. So this goes away, and it just says such that lim D is terminal. So it's what's called the terminal object of the category. It's an object in the category such as any other object maps to it in a unique way. So the terminal object in the category of sets is the one object set. It's a set. The one element set is a set, and any other set maps uniquely to it. And that's the terminal object, and it's also the limit of the empty set. So the limit of the empty diagram. I think I might have said that the one object category is also the terminal category. Yeah.
Is it correct to say that it's all objects without their morphisms?
What is?
The limit of the empty set.
It's all objects without their morphisms. I can't hear what you mean by that.
No.
Yeah, I don't know what all objects are. No, I wouldn't say so. But maybe after we talk more about it, I would understand better. So for colimits in set, there's also a pretty easy description. So, but let's talk about coproducts. You have some set, you have some other set. Their coproduct is like a summary, or maybe like, I don't know, a family photo or something. They're all in there together, and they're all kind of side by side. This is the summary of these two sets. It's the set that includes both of them. There's a map from it into this. The coproduct of these guys is this. And for any other set, if you had a map from this one here and a map from this one here, you'd be able to get a map from that one there in a unique way. The pushout So for pushouts, I have a set A, and it maps to B, and it maps to C, and I want to take the pushout. So someone asked, hey, what is a pullback? Is it just this shape? And again, and it was, and again, the pushout means the colimit of a diagram of this shape. That's all it means. So we're looking for the colimit here. We're trying to find the universal thing. In some sense, if you were being pedantic, you would say, or if you took that definition literally, we're looking for something of the shape colim equals colim equals colim, and map like this, such that all diagrams commute. But if you kind of crush these into one, just think of this as one thing called colim, and you kind of think of this as more of like a cone, then it's the same idea. It just kind of compresses that idea. Okay, so we're looking for a set that absorbs or contains a summary of these three sets and the maps between them. Okay, so what is the colimit of this? It's got to be some set, and it's got to contain copies somehow of all these in a kind of good way. It's got to be natural, so it means whatever, let's just try drawing it. So I'm going to need a place for this one to go. But wherever it went, by the naturality, by the fact that this has to commute, this dot has to go to the same place. But if this dot went here, then this dot has to also go to the same place, because this one needs to commute. But if this dot went here, then this one has to go to the same place. So that's there, and now this one's there, and now this one's there, and now this one's there. And, okay, but that's it. This is supposed to be as free as possible while making all those things commute. So now it needs a place for this one to go, and it goes there. And now this one goes there, and this one goes there. And now we still need a place for this one to go. So we get that. And that's the colimit. That's the summary of this. So all these like people in the family can see themselves in here, but the relationships are preserved or something. I don't know. Any questions about the colimit of this diagram and why it is this? If you think you have a colimit, my job is, so there's this kind of game semantics. This is not about colimits, it's just about logic. The game semantics of logic is, whenever you have a for all exists alternating formula, and then a property at the end, you're the exist, if you want to prove this thing, you're the exist player, and your opponent is the for all player. You also have to prove the property at the end. So, what I'm saying is there exists something, so I present it, that's my job, such that, with maps from these guys' things, so I present that too, such that for all other ones, that's you're allowed to present any set in the world, together with maps from these three things making the diagrams compute, that's the for all, you present that. There exists a unique map from mine to yours making this compute. So no matter what, if someone had an idea, what they thought the colimit was, it's my job as the prover that this is a real colimit to produce a map from mine to yours in a unique way, no matter how you find maps from these three. And the reason it'll work is because if you made sure that all these diagrams commute, and I already did, I have no information in mind except the necessary stuff, so I just know where to send everything. Like, where am I going to send this point? I'm going to send it wherever you sent this point. Good. Right. Okay, any questions about colimits? This is the pushout, and I guess I only have 1 minute left. So I'll just tell you what about colimits in the category of categories are. Colimits in the category of categories, here's a category, here's a category, and here's a category. And there's a functor from this category to this one and this category to this one. So when I take the colimit, it's got to be a new category, and it's got to be able to interpret all the dots and all the arrows in here. So the colimit, does anyone have a guess? How many objects does the colimit category have? So by the way, this one is going there, this one's going there, this one's going there, this one's going there, there, there. When I take the push out of the objects, it turns out I get 3 again. And I also need a place for this morphism to go, so it needs to go here. And I need a place for this morphism to go, so it goes here. And that's the answer. This is the push out in the category of graphs. But the only reason why I think this is a little bit interesting is that all of a sudden there was no morphism from here to here in the original, no morphism from A to C in any of these. And yet in the push out category, a morphism from A to C emerges. So it's kind of like the push out category kind of takes the push out of each of these three, kind of takes the push out of the objects and the morphisms, but adds in the composites automatically. Yes?
It seems like the emergent affects Fong and Karen.
Yeah, it's kind of emergent. It's like saying, I know I need to have composites, so I will just add them whenever whenever I see two composable morphisms, like the one came from here, one came from here, then I guess you could call it emerge. One emerges, the composite emerges because it has to. So in fact, it's really easy to take limits of categories, but to take colimits of categories, it might look easy from this Hasse diagram, but in some sense, it's a more difficult computation. Anyway, so that's the story of limits and colimits. Any questions? Okay, so next time we'll talk about cospans and what any of this has to do with pictures where you draw lots of circles and you put things together. Basically, what's going to happen is that these will be pictures of what are called cospans. And when you compose them, when you put little dot circles inside of circles, and you erase these outer circles, we're going to be using colimits to do that. And the story of circles inside of circles and diagrams inside of diagrams, it will be waiting for you tomorrow.